Hey class, this is, I guess, kind of a review video in a rush. One of the things we were going to do today, but didn't get to do because of the snow day, is you were going to work in your groups on the third homework assignment, which had to do with biological molecules and especially electronegativities. And while working in groups, you were going to get feedback from me. I know I wasn't going to be able to grade this assignment and give it back to you before the exam, but I was going to be able to walk around the classroom and help you. So I do want to discuss this homework, and I know that this means that you'll just all get it right, because I'm just going to show you how to do these problems here, at least a large portion of them, but that's not really my concern because you see the way I've set up this class, these homework assignments count for very, very little. Hardly anything. It's really the exams that matter. So giving away a homework assignment isn't going to affect your grade that much. It's improving your performance on the exam that matters. So let's just look at problem 1 here. The electronegativities of hydrogen and carbon are equal. Using that information, deduce whether hydrocarbons would be hydrophobic or hydrophilic and explain. Remember, a hydrocarbon is just a molecule with a whole bunch of carbons and hydrogens. You need to remember that carbon makes always 4 bonds. Why does carbon make 4 bonds? Because it has an atomic number of 6. So carbon, atomic number of 6. What does that mean? It means it has 6 protons, right? 6 protons. And that means it attracts also 6 electrons because each proton is positively charged and attracts 1 negatively charged electron because opposites attract. Now you also have to remember to answer this question how the electrons arrange themselves. Remember, the first electron shell can only hold 2 electrons around an atom's nucleus, and the second electron shell can hold 8 electrons, and the third electron shell can also hold 8 electrons before it's full. And we never went above that. There are, there are bigger elements with more shells, but it doesn't really pertain to us in biology, so we've just stopped there. So carbon has 6 protons, which means it has 6 electrons. So how do they arrange themselves? Well, they're going to, so if this is carbon with its 6 protons in the nucleus, the first 2 are going to be in the first shell because, like we just said, the first shell can only hold 2 of those 6. And that means there's 4 left. So we have to put them here. And remember, electrons repel each other. It's kind of this weird contradiction. I know it's kind of difficult to understand. I have to move my microphone. I'm sorry. This isn't going to be perfect because I'm just having to do this in a rush. But I know that there's this seeming contradiction where electrons pair up, but they also repel each other. They do pair up. They pair up to become stable and to have a full outer shell, but they don't pair up unless they need to. So there's space for 4 pairs, but there's only 4 electrons, so none of them are paired. So each of these is missing its pair. This tells you that carbon needs to share 4 electrons from other atoms, from other sources, in order to fill its outer valence, because remember, atoms interact with each other. This was on your last homework. Atoms interact with each other in such a way that fills their outer valence. So it wants to fill up that outer valence. It wants to fill those 4 empty slots. It's got to share electrons with 4 from 4 other sources. This means it needs to form 4 covalent bonds, because covalent bonds are how atoms share electrons, and it needs to share 4 more from other atoms. So 4 slots equals 4 covalent bonds. I'm showing you carbon as an example. You can do this with any element. You just figure out what's its atomic number. To figure that out, you just look at a periodic table. I know carbon is 6 off the top of my head just because I've been a biologist for a while. But if you don't know off the top of your head, get a periodic table, and I will always provide periodic tables in an exam where I expect you to figure out these things. So you look at a periodic table, find the atomic number. That tells you the number of protons, which tells you the number of electrons that this element is starting with. You figure out how they're arranged, figure out what's missing from the outer valence, because they like the outer valence to be full. That's going to tell you how many bonds this particular element can make. Carbon always forms 4 bonds because this is always its starting situation, right? Okay, So that's the background, and I know, I'm trying to create a review out of this. Okay, so the electronegativities of hydrogen and carbon are equal. This means you answered questions about electronegativity in your last homework, and you all did so phenomenally on that. So I know you understand that electronegativity describes how strong an element is in its attraction for electrons. So if carbon and hydrogen are approximately equal in terms of their electronegativities, what that means is that they're equally sharing electrons. So their electronegativities are equal. That means equal sharing, equal electron sharing. Okay, and that's going to and what is a hydrocarbon? What is a hydrocarbon? It's just what it sounds like. It's hydrogen and carbon. It's just like strings or rings of just hydrogen and carbon. However they go, they can be strings where it's just a bunch of carbons strung together with, surrounded by hydrogens. Remember, carbon forms 4 bonds, so each of these has to have 4 lines. Each line represents a polar covalent bond. A pair of shared electrons. One of the electrons in each pair comes from the carbon. The other comes from the hydrogen or the other carbon or whatever it's attached to. So this is an example of a hydrocarbon. It's just something with carbon and hydrogen. And we just said that carbon and hydrogen have equal electronegativities, which means they have equal pull on electrons. They're equally sharing these electrons. So what kind of covalent bond is it going to be? If there is, and again, you just did this in your last homework beautifully. You explained to me what a polar covalent bond is. A polar covalent bond is when 2 atoms with not equal electronegativities are sharing electrons and they're sharing them unequally. That's a polar covalent bond. So is this going to be a polar covalent bond? No, because they're equal electron sharing. So this is a non-polar covalent bond. Every hydrocarbon is filled with nonpolar covalent bonds. This carbon and this hydrogen have an equal enough sharing of electrons to be considered nonpolar. Nonpolar. Carbon and carbon. Carbon is as strong as carbon, right? Because it's the same thing. So nonpolar. These are all nonpolar covalent bonds. Okay, so that's the first thing you do. So you figure out what kind of bond it is. It's a nonpolar covalent bond. Now you have to figure out, is it hydrophobic or hydrophilic? Okay, so that has to do with its relationship with water. Hydro means water. So hydrophobic, you know what a phobia is. That describes a fear that someone has. Phobia means fear. So something that's hydrophobic is a molecule that's water fearing. Obviously, these molecules don't have emotion. That's like sort of an emergent property of animals, right? So they don't have, the molecules don't have emotion, so they don't literally, it's an analogy. They don't literally fear water, but they're always moving away from water. So a molecule that's hydrophobic separates away from water. And what's philia? Philia or philic refers to love. So something that's hydrophilic, that's a molecule that loves water. It dissolves in water. It's attracted to water. So things that are hydrophilic dissolve in water because the water molecules are all attracted to it. So think about salt. When you drop a crystal, if you dropped a big old crystal of salt in water, it would dissolve. Why? Because every little molecule of salt is going to be positively and negatively charged, and opposites attract. Water molecules, remember, have positive and negative charges, and so the opposites, the negative charges on the water molecule just love the positive charges on the salt, and the positive charges in the water molecule just love the negative charges on the salt, and they're attracted to each other. That's the philia part. That's the loving part. Again, remember, these molecules don't have consciousness. They don't have like a neural network. They don't have the chemicals of love like oxytocin and dopamine and all of that. This is all analogy in these words, but they help us remember. So things that dissolve in water are hydrophilic. Things that don't dissolve in water are hydrophobic. So we just said that this is nonpolar. Nonpolar. That means no negative charges. There's equal sharing of electrons. So you don't have clusters of electrons in one part of the molecule and an absence of electrons in another part of the molecule. No, they're just nice and evenly spread out. Remember, every one of these atoms has protons in the nucleus, and all the electrons are evenly spread out around all the protons, and so it's neutral. There's no collection, there's no clustering of negatives and positives anywhere. So this is a neutral molecule. It has nothing to attract water. Remember, water, and if you need to review the chemistry of water, remember all my lecture videos up to this point have been online, available to you. If you need to review the chemistry of water to understand why water has positive and negative regions, please go to the water chemistry video. Also, I discuss it in polar covalent bonds in the chemical bond video. So this is hydrophobic. There's nothing to attract water, so it separates out, okay? Hydrophobic. Water is attracted to itself to the exclusion of these nonpolar, non-charged neutral molecules. If you want to, sorry, I'm having my lunch at the same time. So if it helps you to have these analogies, think about water as really liking things to be exciting. It likes to have a valence on, a charge, a signal. It needs a signal on the molecules that it's attracted to. It's a little bit bipolar. It's a polar molecule. It's bipolar. It has extreme positives and extreme negatives, right? Not that extreme, but it has these positive and negative regions. And it's not attracted to neutral things that are just flat and boring. It wants to be attracted to things that are also very positive or very negative, or even slightly positive and slightly negative. So these nonpolar molecules that are neutral are not interesting to water. It's excluded by water. They're hydrophobic. They don't dissolve in water. Okay, question 2. The chart on the next page indicates the electronegativities of different elements. The higher the number, the more electronegative the element. Based on the information in the chart, which of the following would form a nonpolar covalent bond? Choose all that apply. Okay, so in this question, we want to circle the entire pairing. Okay, so hydrogen bound to sodium. Okay, this doesn't happen very often, but let's just take a look. So we're circling what would form a nonpolar covalent bond. So equal sharings. What would have an equal sharing? Okay, sodium and hydrogen. All right, where's sodium? Here's sodium. Sodium is down here. And hydrogen is here. Is that equal? No. I chose this electronegativity chart because I like the color coding, because you don't even have to look at the numbers. If something is the same color, they're about equal. If they're different colors, they're unequal. So sodium and hydrogen, unequal values. They're not going to share electrons equally, so that's going to be polar. So we're not going to circle it. Actually, I'm just going to skip down to D, oxygen bound to oxygen. Obviously, oxygen is equally strong as oxygen, so we're just going to circle that. That's nonpolar. Equal sharing, nonpolar. Okay, how about hydrogen to nitrogen for B? Let's just check. All right, these are the electronegativities. There's hydrogen and, what was it, nitrogen? Are they the same color? No, different. Not equal. So that is a polar covalent bond because there's not equal sharing, because they're not the same strength. They're not the same electronegativity. How about hydrogen bound to boron? All right, there's hydrogen, and where's boron? There it is. Hydrogen and boron, that's equal. Same color. Of course, they're not perfectly the same. They're just like, everything's on a gradient, right? I mean, they're not perfectly equal strengths, but they're close enough. So this is nonpolar, equal sharing of electrons, no clustering of negative charges anywhere. And finally, oxygen to phosphorus. There's oxygen, and where's phosphorus? P. Okay, so oxygen and phosphorus. Nope, unequal, different colors. That's a polar covalent bond. We only have 2 nonpolar covalent bonds here. Equal sharing. Equal sharing of electrons, because they have equal electronegativities. Electronegativities. If you feel like you don't even know what electronegativities are, please refer to my prior videos on the chemistry section. All of them are recorded online. So that's why I don't know what to provide you for review, because I've given you all of my lecture videos already. So if there's something that's not in there, I don't just like know that off the top of my head. You need to like let me know. Okay, so in the same list for the elements forming polar covalent bonds, identify which of the two elements would be partially negative. So now we're looking at the ones that are polar. These are the ones we crossed out before. Polar covalent bonds, the ones that have unequal sharing. That's going to be this one, and this one. So have unequal sharing. I want to know which one in each of these pairs would be partially negative. That's the one that, because what are electrons? Electrons are negatively charged. So the one that's negative is going to be the electron hog, the one that's keeping all those negatively charged particles around it. So the one that's negative is going to be highlighted in red. And so if I do that, that's going to be here. Red is negative. And in blue, we have positive. Okay. The ones that are positive, remember, every atom has positively charged protons in its nucleus, so the ones that don't have the electrons to balance it are going to be partially positive, right? The electrons go away from the positive ones. They're positive because they can't hold the negatively charged electrons around them to neutralize them. Okay, so just in the ones that are starred, because those are, remember, these are the ones that were polar. We've already done that question, so we don't need to think about these anymore. We're just talking, or the ones that are nonpolar. These are the ones that are nonpolar. We're just working with the polar ones now. Okay, let's start with blue, because I'm already in blue. Positive. So all you need to do, so electronegativity is the strength of attraction to electrons. So in a polar covalent bond, you have one with a high electronegativity and one with a low electronegativity. The one with the high electronegativity is really strong in its pull on the electrons. That means it's going to be negative. The electron hog will be negative. And the one that's not strong is going to be losing its electrons, leaving its positive charges in the nucleus unbalanced. And so those are going to be the positive charges. So positive charges in blue. So let's look at hydrogen versus sodium. Hydrogen versus sodium. So here's the hydrogen again. And where's the sodium? Let me clear all this. Okay. Yes. Okay. So sodium, there it is. I couldn't see because of all that. So hydrogen and sodium. Which one is lower? Well, the sodium's lower. That's going to be the blue one. Okay. So just to it has an electronegativity of 0.9. Hydrogen has an electronegativity of 2.1. Which one's bigger? The hydrogen is bigger. 2 is bigger than 0.9. So this one is weaker. It's losing its electrons, which means it's positively charged. The electrons are negative and the protons are positive. So this is going to be the positively charged one. Okay, now let's go to hydrogen and nitrogen. Oops, hydrogen and nitrogen. So there's the hydrogen again, there's the nitrogen. Now which one is stronger? See, it's switched, right? Hydrogen was the stronger one in this pair, but it's the weaker one in this pair because it's hydrogen's 2.1 for its electronegativity, and nitrogen is 3.0. 3 is bigger than 2. So now hydrogen's the weak one. Hydrogen's losing its negative electrons, leaving it positive in this pairing. You see, it's just comparison. You can't always know off the top of your head which is going to be keeping electrons, which is going to be the electron hog. It's all relative. It's like I'm stronger than some people and weaker than others. Well, same with these elements. Okay, oxygen and phosphorus. So here's oxygen, and where's phosphorus? It's here. So oxygen's the hog, phosphorus is the weak one. So the weaker one is going to be positively charged because it's losing its negatively charged electrons. Okay, so then, hydrogen was the strong one here, so it's more electronegative. It's keeping those negatively charged electrons, so it's negative. Nitrogen is the strong one here. Oxygen is the more electronegative one there. All right, so that's that problem. Okay, so of the 6 functional groups commonly found in organic molecules listed in your textbook, oh, and you know what? This may be, I'm not sure that that's still correct. We've had there's been a recent update on the textbook, and then the table numberings get all mixed up. So I'm not positive about that. I'm just going to cross it out. But I gave you a chart in our PowerPoint, and I know there is a chart in this chapter. So just find that chart of functional groups. All right, so in the 6 functional groups commonly found in organic molecules, list those that are hydrophobic, do not dissolve in water. Okay, so the ones that we talked about in class were, let's see, there was phosphate. Actually, I'm going to do a different color here because I'm running out of space. Actually, let's just do this. Okay. All right, so functional groups. Maybe I'll do green here to really separate what we're doing. Okay, so let's do, there was a phosphate. Phosphate is something like this. Sometimes it's drawn with OH, sometimes it's not drawn with OH. That's a phosphate group. And then it's attached to the molecule here. There's a methyl group, which is attached to whatever the organic molecule here. There's let's see, a hydroxyl group, which is O attached to H, attached to the organic molecule here. There's amino. Sometimes this has 3 H's and a positive charge. Sometimes it has 2 H's. This one, the amino groups are quite dynamic in that way. And then, let's see, we have carbonyl, carboxyl groups and carbonyl groups. So the carbonyl groups are carbon with oxygen and an OH there. So this is carboxyl, and it's attached to the organic molecule here. You find amino and carboxyl in amino acids. Just a carbonyl group by itself just has an O there. It'll be attached to an H. And the organic molecule here, remember carbon's always making 4 bonds. I think, let's see, 1, 2, 3, 4, 5, 6. That's all we did in class. I think your textbook might have a sulfhydryl group, something like that. We didn't cover it in class, but that's another possible. There's more that, it just depends on what you want to classify. I limit it to the 6 on the left here because those we really see the most often in organic molecules. So the question is, which of these are hydrophobic or do not dissolve in water? A hydrophobic molecule has no clustering of electric charge, which means the electrons are spread out evenly over all the protons, which means there's equal sharing. So you're going to find hydrophobic functional groups and hydrophobic molecules always have equal sharing of electrons. So to figure out which ones are hydrophobic, you again have to look at the electronegativity chart and look to see whether all of these are equal. Actually, in this phosphate group, you don't even have to do that. You see that there's a negative charge here. That means it dissolves in water. Okay, so it's got a negative charge, and water is attracted to both negative and positive. So this we can immediately cross out. It is hydrophilic because it has a positive or negative charge, in this case a negative charge, that attracts it to water. So we don't even have to look very hard at that one. All right, how about carbon, hydrogen? Well, I just explained in the first problem that carbon and hydrogen have equal electronegativity, so they have equal sharing of electrons. That means that the electrons aren't clustering anywhere, so neutral. This one is hydrophobic. Sulfur, let's just look at sulfur. Again, you don't need to list this one, but if you were to list it, sulfur and hydrogen. There's hydrogen. Where's sulfur? Sulfur. Here's sulfur. 2.1, 2.5, same color. It's actually the same relationship. Sulfur and carbon have the same electronegativity. So this one's also hydrophobic. All right, OH, we already know. I hope you know by now that off the top of your head that oxygen and hydrogen share unequally, because that's the whole reason that, oops, I switched this color and I didn't want to. That's the whole reason that water is polar, is that oxygen and hydrogen, water's H2O, and oxygen is an electron hog relative to hydrogen, so this is polar. Polar dissolves in water. It's got a partially negative charge on the oxygen, partially positive charge on the hydrogen, and that attracts to the positive and negative charges on water molecules, so it dissolves in water. It's hydrophilic. All right, nitrogen and hydrogen. Well, here, we can just look up here. We just checked. We already checked the relationship between hydrogen and nitrogen. We know that it's polar, right? It's got, hydrogen, nitrogen is an electron hog relative to hydrogen. There's no equal sharing of electrons. Not equal sharing, which means it is polar. The nitrogen is going to be partially negative. Hydrogen is going to be partially positive. Again, we have this hydroxyl group, which is the same thing we had here. We know that dissolves in water. Okay, don't even need to look at the rest. Okay, oxygen compared to carbon. We didn't look at that before, so let's look now. Carbon to oxygen. What's their relationship? Okay, carbon's here, oxygen's here, different color, different electronegativities. That means there's a cluster of electrons here, and they're lacking around here. So this is polar, hydrophilic. We just want hydrophobic because I'm asking about the hydrophobic R group. So 1, 2, or if you just answered with the methyl group, that's fine. Okay, so again, all you're doing, so remember, opposites attract. Hydrophilic things are attracted to water. That means it has opposite charges from water. What's an opposite charge from water? Well, anything really, because water has positive charges and negative charges in it. It's a polar molecule. It has a partially negatively charged region and a partially positive charged region. So any positive or negative charge will be attracted to water molecules and will be hydrophilic and will dissolve. The only way for something to be hydrophobic and not dissolve in water is for it to be neutral. Water doesn't like boring neutral things. That's going to be methyl groups, hydrocarbons, sulfhydryl groups. Water doesn't like that because it's neutral. What makes it neutral? Equal sharing of electrons throughout. There's no clustering of negatives or positives. Okay, so the image below is of an amino acid, the building blocks of proteins and enzymes. Okay, let's look over here. And let's get closer again. Okay. Indicate which is the carbonyl, indicate which is the carboxyl group and the amino group, and identify in each of those groups where the partial positive and negative charges are. Again, this is just comparing electronegativities, and we already did this in the last problem. I'm going to go back to blue here. So we were, I want to again erase all this. Okay, so so in the so the first one is I'm sorry, I'm not even editing this video, I hope that's okay. So indicate which is the carboxyl group and the amino group. So this is the carboxyl group, right? And this is the amino group. Okay. And identify within each of these groups where the partial positive and negative charges are. Okay, so let's look down here. So let's compare carbon and oxygen. You just have to look at the pairing, carbon and oxygen. Carbon and oxygen. Oxygen's an electron hog, partially negative. Oxygen's pretty much always an electron hog. That leaves the carbon partially positive. It leaves this hydrogen partially positive. There you go. That's all you need to do. Find the electron hog, which is the one with the stronger electronegativity, and put the negative charge there. And what it's bound to is that's what it's stealing electrons from, so that's going to be positive. Okay, nitrogen. And compare that to hydrogen. Which one's stronger? Nitrogen has the higher electronegativity, so that one's the electron hog. That's partially negative. These are going to be partially positive. All right. And then B, would amino acids dissolve in water? Well, do they have positive and negative charges for water to be attracted to? Yes, I just put those in there. So dissolve in water, yes, it's hydrophilic. Because it's attracted, opposites attract. It has positive and negative charges to be attracted to water's negative and positive charges. What kind of bonds hold water molecules together and allow molecules like amino acids to dissolve in water? Okay, what is going to cause water to be, how is water attracted to this? Well, here's a water molecule, H2O, 2 hydrogens and an oxygen, partial negative charge, partial positive charge, partial positive charge. So what holds all these water molecules together? It's attractions we know between positives and negatives, between opposites. There's just like this force that's attracting them. They're attracting these opposites. We have a name for that force. It's called hydrogen bonds. Okay, same thing here. So if you have an amino acid, so here's a partial positive charge on this hydrogen. And if we had a water molecule, right, there's H2O. And remember, the oxygen is an electron hog. It's partially negative, while this hydrogen is partially positive, and opposites attract. So there's a hydrogen bond, right? And so water molecules will surround other molecules that have positive and negative charges, and that's what causes them to dissolve. And if it dissolves, we call it hydrophilic. Okay. So this is another hydrogen bond. Okay. And then the last question, what is the basic molecular formula for sugars? So remember, we spent a long time in class on this. We said that anything, sugars can have all kinds of numbers of carbons. Usually they are rings of carbon with a hydroxyl groups and stuff sticking out. But it can have any number of carbons. So what makes a sugar and not another organic molecule? It has to have the ratio of CH2O. 1 carbon for every oxygen and 1 carbon for every 2 hydrogens. So that could be like glycerol, that could be C3H6O3. Same number of carbons and oxygens. For every carbon, there's an oxygen, and twice as many hydrogens as carbons. You can have 5, like ribose, like in DNA. OH10, sorry, O5. Again, same number of carbons and hydrogens, twice as many hydrogens as carbons. You can have glucose, that comes up a lot in biology. This is where you get the H12. But you see that the ratios stay the same. 1 carbon to 2 hydrogens to 1 oxygen. This is supposed to be an O, not a 0. Okay, and that's the homework. I hope that's helpful. I'm sorry that you're not going to be able to get any kind of feedback directly before the exam, but I just think that's really important to cover because certainly these things will come up on the exam.